Great, so I guess we'll get started. First of all, hello everyone. Thank you for joining today's webinar. My name is Brian Lieblich and I'm an applications engineer here at Plexim, and I'm excited to present today's webinar on microgrid applications using Plex and the PLECS RT Box. And so my goal is that at the end of this presentation, you should have a feel for how Plex is being used in microgrid and distributed energy resource applications, how it may be relevant for your work, and where Plex fits in different stages of microgrid projects. So from initial concept to detailed design, controller validation, as well as system level tests. So one emphasis in this webinar is going to be on the value of real-time simulation to accelerate the development and deployment of microgrid and distributed energy resource projects. So here's an agenda for today's presentation. First off, I want to give a very short introduction to Plexim, the company, and Plex, the simulation software for those of you who are unfamiliar. Then we'll introduce some key microgrid concepts and some of the challenges in microgrid and DER design, development, and deployment. Then we'll move on to an overview of how Plex tools are being used by engineers to solve these challenges. And then we'll move on to some examples. So we'll look at some demos of distributed energy resource and microgrid models in Plex standalone, where we'll simulate a microgrid on RPC. And then we'll look at real-time control hardware-in-the-loop demo, where we'll connect embedded controllers to several interconnected Plex RT boxes, and we'll simulate a microgrid in real time. Also, I might use a few terms interchangeably here during the presentation. So when I say offline or desktop simulation, it means that the simulation is truly running on my personal computer, whereas online, real-time, or hardware-in-the-loop or HIL indicate that the model is being executed in real time on the RT box hardware, as well as on real physical controllers. So please ask any questions during today's webinar that you may have, either in real time, and we'll try and address them in the chat window, or reach out at the end of the presentation, and we'll always follow up with you at the end. If you want to reach out to us, you can do so at info@plexim.com for more information at any time. So actually, before moving forward into the next Who We Are slide, I just also want to give a quick preview of the setup that we'll be using a little later in today. So for the second half of the presentation, or the RT box setup here, which includes several RT boxes that we're going to have interconnected, as well as a oscilloscope over there to view some signals in real time. So for those of you who are unfamiliar with Plexim, I want to give a quick introduction to who we are. We create design tools for the development and testing of power electronic systems. So we make the engineering software Plex that's widely adopted in industry and academia. So Plex is a complete power conversion simulation package that yields robust and fast results, and it comes in two different versions. So there's Plex Blockset, which operates in the MathWorks Simulink environment, while Plex Standalone is an independent solution. So both feature comprehensive component libraries that include the electrical, thermal, magnetic, and mechanical aspects of converter systems, as well as a controls library for analog and digital control systems. So we've been selling our simulation software Plex since 2002, and we've come out with our own real-time simulation platform called the RT Box in 2016. We also have processor-in-the-loop support, and we recently launched our embedded coder for the TI C2000 microprocessor just a few weeks ago. So we're headquartered in Zurich, and we have offices in Cambridge, Massachusetts, and Seattle, Washington. And you'll see a few different products in today's webinar. So we'll use Plex Standalone to build and explore models. We'll use the Plex coder, which takes these models in the continuous state space and will translate these into ANSI C code that we can execute in the discrete time on real-time targets. And so the real-time target we'll be using in this case is the RT box, which you'll see used in today's webinar. So with that, I want to give a quick overview of microgrids. So just so we have a common language throughout today's webinar. So in the last decade or so, there's been a huge increase in power electronic interface distributed energy resources connected to the power distribution system. And so this, along with the supporting communications and smart grid infrastructure, there are all these controllable assets connected at the distribution level in the grid. And what you can do is you can leverage these to improve the reliability, resiliency of power networks, and then also use these for economic incentives. So whether they provide grid services such as peak shaving, or they may offer, say, deferred investment cost for utility. So a simple diagram of an AC microgrid is shown on the right-hand side of the screen, which consists of a set of interconnected loads and distributed energy resources. The entire system up to the point of interconnection can act as a controllable entity with respect to the grid. And so it can operate either connected to the grid or disconnected to the grid in an islanded mode. So there's several different types and applications of microgrid, different AC, DC, and hybrid topologies, and lots of end users and use cases. Additionally, many of the technical challenges, principles, and control approaches that apply to microgrids also apply to small isolated electrical systems, so island power systems or shipboard or aircraft systems. So in this webinar, we'll be focusing mostly on three-phase AC system for utility applications. So looking closer at our hypothetical microgrid, we'll see that there's a range of systems from conventional electric loads to several types of distributed energy resources, or DERs. So each one of these systems has their own local controller and may have several layers of controls. So for example, if we consider a small distribution connected wind farm, there'll be several turbine level controls, so DC bus regulation, rotor and grid side converter controls, as well as park level control loops that maybe will regulate the voltage and frequency at the point of connection. There'll also be, say, protection systems, and then there's this communications infrastructure that links all of these systems together. And so interacting with these different local controllers is a microgrid controller, and it contains the core microgrid functionality, for example, handling islanding transitions or say setting real-time dispatch, and basically deciding what each element in the microgrid should generally be doing at any given time, and then how all of these resources can coordinate to achieve a common objective and respond to disturbances. Then typically there are also higher level functions such as distribution management systems that will coordinate with the DSO, energy markets, and so on. So this proliferation of control and communication is also one of the main technical challenges in microgrid development. And so there's this change in power systems that were previously dominated by the physics of synchronous machines to systems that rely on controls and software. And so while these can be incredibly powerful and flexible, underlying each one of these control systems are thousands of lines of control code that have to be validated. And so how does each control function perform independently? And then how do they interact electrically during disturbances and faults, but then also how do they interact in the cyber physical domain? And how robust is the overall system to different disturbances such as non-dispatchable generation, and they coordinate to achieve their control objective. So all these problems and challenges are also exacerbated in small electrical islands. There are also several other technical challenges. So for example, grounding, protection, the whole controls aspect that you can investigate in Plex, but they're beyond the scope of what we're talking about today. So another point to drive home is that the power system and controller phenomenon that are happening in these microgrids cover a wide range of time constants. So it makes simulating these systems, especially in real time, fairly challenging. So there's phenomena on the order of a few nanoseconds that need to capture. So for PWM switching transitions, there's transients on the millisecond range if we're considering inverter intercurrent control loops, phase lock loops, certain protection functions, and then things happening, say, on the order of seconds. So whether you have your voltage and frequency controls, there's the mechanical time constants of your systems and machines, and then you have longer items, say, such as daily load variations or battery cycling. So from a pure simulation perspective, simulation speed is critical when you're looking at running hundreds of test cases or investigating these longer duration phenomenon. So that's one of the strengths of Plex. And then for real-time simulation, you need a simulator that's flexible and has sufficient model fidelity to capture all these critical details happening on the short end of the time spectrum. So just summarizing, some of the big technical challenges here are designing and testing each controller extensively, so both as an independent unit and then as part of a larger system, and seeing how they all interact and being confident in your model fidelity and test coverage. And another issue we've heard about quite a lot is getting controller models, especially detailed models from different software and different hardware vendors. And so understanding what the underlying approximations are and having confidence that all of your models are accurate and will represent the system deployed in the field. So early on, there's definitely value for using generic models, and we'll talk about an example of that today. But to really validate the system performance, controller hardware in the loop becomes a powerful tool to ensure that your testing is accurately capturing the real controller behavior. So when you actually deploy the project, say you can use exported parameter sets from the software, and you can use benchmarked firmware versions, compare that to what's in the field, say versus there being some obscure scaling factor hidden deep in your model or code. So it's also worth mentioning here that what we're working towards is confidence that our DER and microgrid projects and controllers will comply with relevant standards. So for example, IEEE 2037 and 2038 for microgrid controllers and IEEE 1547 for DERs. And what that really is working towards is ensuring that you have a successful project operating in the field. So how can Plex be used to work towards that goal and to tackle the challenges we just outlined? So generally speaking, there's two key ways of this. There's offline simulation, which is the traditional way these systems have been studied, and then there's hardware in the loop, which is used to test real physical controllers and physical systems. So starting with offline simulations, Plex simulation software strength has typically been to design power conversion systems, so detailed converter and electrical control models. And so naturally, you can start to connect these power converters into larger and larger systems. One thing we're seeing also used quite a bit in this offline simulation stage is software in the loop. So we'll see people design and test or prototype their C control code in Plex, and then port that over into their embedded control environment, or they'll package existing control code into a C script or DLL, and then run a software in the loop simulation that way. So the other use case for Plex tools is in hardware in the loop simulation. So we have, again, real physical hardware interacting with a virtual model running in real time in the RT box. And so on the right-hand side, everything within that blue barrier is what's running on a real-time simulator, solving the complex set of equations that describe this power conversion system, and then it interfaces with the control hardware shown in red. So a set of analog and digital signals and PWM signals are exchanged between the controller and RT box. And then on top of that, you may have a microgrid to DER control interactions that are all happening in real time on actual control hardware, but they're looking at this virtual plant. So this way, different processor-specific quirks, implementation issues, as well as the control and communication systems between local DERs and the microgrid controller can all be tested in real time. So it's also important to note that these tools have applications throughout the project cycle. So from conception to design to test and through operation and maintenance. So in early project conception, you may be asking questions like what microgrid topology is best suited for my needs? And how can I sketch out, say, different power stage and control topologies and see what insights we can gain that way? So we can take these and maybe turn them into system or different subsystem specifications. And then simulation has a powerful role to play in the detailed design and prototyping stages. So to actually develop controllers, design and evaluate test cases, and leverage tools like software in the loop. And then as we move on forward into the implementation stages, we can say benchmark and refine our model against lab or field measurements. And as we start testing actual hardware in the subsystem and system testing, Hill has an increasingly important role to play to validate the control and communication architecture, maybe even up to running pre-commissioning tests on a real-time simulator before moving on to full power commissioning. And then lastly, both offline simulation and Hill models can be used throughout the operation of the asset. So in the event of, say, a field failure, or in terms of feature development or system expansion. So it's also worth mentioning that the same Plex model can be reused and iterated on and developed as you progress through these different stages in your overall design. So in this webinar, we're going to look at two models in detail, and one is further on the ideas, concepts, the initial conception of a project, and then the second one is representing, say, a platform for early controller integration testing. So before moving into depth on these two microgrid models, I do want to mention that the Plex demo model library has some great examples of how different DR topologies can be simulated and controlled. So a quick highlight of these would include a single phase and three-phase PV model. There's this DFIG model on the right-hand side, and that's a good reference to learn about the different Plex domains, so thermal, magnetic, mechanical, and then highlights how these turbines respond to a low voltage ride-through grid code requirement. So also, if you're a Plex user, you know that these demo models always contain some little valuable nuggets in terms of how to implement different types of controllers, create mass subsystems, and other little tips that might be useful in your next model. I also want to mention a new video that you can watch in our Plex Model of the Month video series. So this is a user-submitted model, and it shows a decentralized PWM carrier interleaving approach that's applicable to DC microgrids. So it's an interesting research application, and it uses nonlinear oscillators in each one of these local controllers to achieve communication-free switch interleaving. So the offline simulation model that we're going to be looking at in a bit more detail today is a microgrid and island operation that was developed and shared with us by Dr. Louis Garces. And so we're going to go to Plex and look at this in more detail. So this model is also included in the demo model library. And so if you want to open up your Plex application, please do, and feel free to navigate along with me. So now we'll navigate into Plex, and we can go into the demo models. This is in the power distribution, microgrid and island operation. And what you'll see here is just a brief description of the model. And if we click on this Plex model link in the upper right-hand corner, it will open the model that we want to look at. And so this is an example, as I said, of early proof of concept study in Plex. So the main motivation is to test this proposed control topology for a microgrid and see how it performs while operating in islanded mode. And so structurally, we'll see that it's similar to the model, the prototypical microgrid we were looking at earlier. So on the left-hand side, we have 3 voltage source inverters. Over here, we have a small load, and then we have the supervisory controller. This point of connection, there actually is operating only in islanded mode, so there is no utility connection in this model. In terms of sizing, we'll actually notice that each one of these 3 generation resources are sized slightly differently. And so you have a 1 MVA, a 500 kVA, and then a 200 kVA controller. So in here we have these local controllers, and so these receive a voltage set point and a frequency set point, and then out of these controllers come a real power measurement and a reactive power measurement. And what this is on top of these is a droop controller. And so in a it's meant to mimic the behavior of synchronous generation. So if we look at this largely inductive network, what ends up happening is that the real power flow out of this converter is dominated by the phase angle difference between the converter terminals and the point of connection. And then the reactive power output is largely a function of the voltage at the terminal of the converter and then the point of connection as well. And so with real and reactive power output decoupled, we can decouple their control. And so we droop the frequency set point of the converter as a function of the real power output. And then we also do the same thing where we take the voltage set point of the converter and we adjust it based on the reactive power output. And so these droops are coordinated so that all these loads, all these generation resources share the load equally. So one thing to note is that this is a generic model. And so if we were to look underneath this system, we'd see that it's underneath the mask, we'd look and see that everything's implemented here in open loop. And then this is an average model. If we look underneath this mask, it's just an average 3-phase VSI. So the idea here is even with these very simple open loop models, we're starting to get an idea of what type of controls work for our system. So next, we'll just take a look at the supervisory controller. And what happens is that this supervisory controller senses the conditions at the point of connection, crunches some numbers, and then sends a voltage and frequency set point to each one of these local droop controllers. And so this is responsible for trying to achieve a global regulation goal at the point of connection. So if we just were to look underneath this subsystem as well, we'll see that how this is implemented. And so what there is this voltage at the point of connection is transformed through a simple PLL into a frequency at the point of connection, as well as a voltage magnitude. And then the error between the desired frequency at the point of connection and this measurement is then translated into a set point that's sent out to the converters. There's also this switch function here that just will enable or disable the control, and it'll just send a nominal value before this enable function is turned on. The other point to note is that these are also heavily filtered. And so this is, again, representing, say, the communication latency between this supervisory controller and then all of the local controls. So the references are changed very slowly in simulation. So having looked at the model, let's run it really quickly. And we'll see over here on the left-hand side, so each one of these converters have a little display just showing the real and reactive power output. And the upper value is in watts and the lower one is in per unit. And so this is shown for all of them. And so there's 3 different time frames of interest that we're going to look at. So between 0 and 1 second, we're having the droop controls disabled. And so each converter, in terms of its set point, its open loop set point, is just receiving the nominal frequency and voltage. Then at 1 second, this droop enabler function will be active. And then at 10 seconds, we'll enable the supervisory controller. So let's look and see how this looks in simulation. And so if we start and look at it in the beginning, we'll see that before the droop controls are enabled, each one of these converters is working at different output levels. And this blue one up here is the 200 kVA inverter. And so it's operating right about at full output, whereas the 500 kVA and 1 MVA converter aren't working as hard. And so at 1 second, the droop controls are enabled, and we'll see that load balancing between these different resources happens. So they're all loading at approximately 50%. And so we'll see that the load is balanced, but the conditions at the point of connection actually deviate from their nominal values. And so we'll see that the droop controllers sag the voltage down at the point of connection from nominal as well as the frequency. And so it stays like that until this supervisory controller is enabled. And what it does is it elevates the voltage and frequency references sent to each one of these converters. And so it actually increases their real power output to compensate for the decrease in frequency, much like a synchronous generator would. Summarizing this, we can see that these global regulation goals are achieved, and that this model, even though it's so simple, is a really powerful way to prove that this proposed control architecture can work and manage sharing load between the inverters through a droop control, and then achieve these system-wide goals through the supervisory controller. And it does all of this while abstracting away a lot of these low-level converter details. So the results of this model, again, are valuable inputs that can be fed into the specification of the overall system, and then utilized in the detailed design stages of the microgrid, and see how we can refine these concepts into actual implementations. So I'm going to transition back to the slides very quickly. And up next, we're going to look at a real-time model of a simple microgrid running on the RT box. And so again, the motivation here is to test a controller that's closer to its final implementation, and say during development and before being deployed into a larger system. So first, we're going to look at the structure of the microgrid model, both electrically and then how we approach this from a real-time simulation perspective. So this is the structure of the model, and starting on the upper right-hand side, we can see a stiff grid source that represents the utility, and then there's a bit of impedance connecting that to the point of connection. So say representing a distribution transform impedance, which tends to dominate the impedance up to that point. So, and then we have a synchronous machine at the point of connection, and it's driven by a constant excitation and torque source, say representing a diesel engine. And then below that, we have an adjustable load that we'll be manipulating in simulation. Then on the left-hand side, there's several voltage source inverters that are connected to the grid with an LCL output filter. So each one of these inverters is an NPC converter rated at about 20 kVA with 5 kilohertz switching frequency. And so the switching ripple is going to be at about a 10 kilohertz. And then we'll also notice that there's a bit of impedance between each one of these voltage source inverters, say representing a distribution line or cable that connects these resources. So what we're going to test in real time is the integrated performance of this network, and look at the inverter controllers, and then also we'll add some disturbances via the synchronous machine inputs and the load. So in this case, how we're actually going to approach this from a simulation perspective is we're going to split this model across multiple RT boxes and show how the RT box hardware can be interconnected to model these larger systems. So we'll use a total of 4 RT boxes in this demo that I showed earlier. So in this particular model, there's a few motivations for this. So firstly, each VSI controller uses 14 analog signals, which utilizes the bulk of the analog outputs of a single RT box. So in order to have multiple inverters, multiple RT boxes are required. The second motivation here is model complexity. So the inverters are modeled as switching converters, and so you'll be able to see the high frequency current ripple on the output. And in order to get this level of fidelity, especially at the voltage source inverter level, we need a very small simulation time step. So it limits the overall complexity of the model that we can execute in real time on a single RT box. And so we overcome these limitations by interconnecting these RT boxes as shown here. So we have the grid source, synchronous machine, and the load on one RT box, as well as the system up to the capacitor of the LCL output filter. And then the boxes, the voltage source inverters have the VSI, the 3-level MPC, and then the LC portion of the LCL filter. And so the reason that we're splitting this model here is that it's a natural point to split the model. So there's a fairly stiff voltage source at the capacitor terminals, and then a fairly stiff current flow on that grid side inductor. And by stiff, I mean that the current and voltage, they don't change drastically from time step to time step. They're fairly low ripple signals. And so they're largely power frequency in nature. And so we'll look at how this is implemented in more detail once we actually open the model. So I also want to show how these systems are interlinked. And so on the rear of the RT box, there are 4 fiber ports, or SFP ports, we'll also call them. So each RT box has 4 SFP ports that can be connected to another unit. And so here the grid RT box has a point-to-point high-speed communication link with VSI A, VSI B, and C, as shown. And it's also worth noting that there are different tree-like structures that can be implemented here. And so, for example, if VSI A had a separate DC-DC converter that required modeling on another RT box, we could simply connect another unit to the B fiber port on VSI A. So now, again, I'll transition back and just turn on my webcam and show you how this is actually implemented in a hardware setup. And so while the webcam is on, you can actually adjust how large it is by moving a horizontal or vertical slider on your screen to make it a little bit larger. So here we have 4 RT boxes, they're stacked. And so on the uppermost one is the grid box, which just contains the synchronous machine, utility source, and inductive and resistive elements. And there's no controller attached to that. And then underneath it, we have VSI A, B, and C, and they're all connected and back through these SFP links. And then sitting here in each one of these is our controllers. And so we have one is actually a hand-coded controller, And then these two controls, B and C, we're actually using our code generation tool. And then they're connected to the RT box with a launchpad interface board. And so it just maps the PWM signals to digital inputs and the analog outputs to the ADC to the converter. And then there's a few other little benefits, like there's some B and C connectors and switches that we'll be adjusting today. So there's also a scope on the left-hand side, just saying that there's a few measurable signals that we'll look at once the model's up and running. So with that, I want to give a quick overview of how this is actually implemented in the model. And so I'm going to open up Plex real quick, and I'm going to open the model we'll be looking at today. And so this is the structure of the model we were just showing earlier, and this is how this is represented within Plex. And so we can see here these same subsystems. So there's the grid model, the VSI A, B, and C, and then a controller for each converter. And the model deployed to each RT box is contained within its own subsystem. And so this contains everything that we'll be deploying to the grid RT box and the different voltage source inverters. And we can see here at the terminals are different signal connections between these boxes. And what's neat is that this actually represents the information exchange between these units. And so we know that the way that the grid box interacts with these other boxes is through these SFP ports sending information in and out. And so we're actually modeling that in Plex. And then similarly, these are received by VSI-A. And so this model structure basically is a good way for us to subdivide our model into systems that make sense and show the boundaries between them and how they interact. So similarly for VSI-A, we have these voltage measurements and current measurements that come out as analog signals from the RT box. They're fed into our controller, which we model here. And then these PWM signals are actually actuating the digital inputs of the RT box. So these Q signals marked here. And then there's a few other digital signals as well. So with that, let's look at a few different subsystems, and we'll see if we open up just VSI-B, and we can actually see how this is implemented. And we'll look at the power stage and look at just some of the signal mapping. So first of all, here's our 3-level NPC signal. So we can see that these Q PWM signals are then sent in to modulate the 12 switching signals for the VSI. And what's used here is a PWM capture block. And so what this is it's our approach to kind of decouple the execution time or model step size of the model with sensing these PWM signals, which we need very high fidelity to capture. And so what we utilize is actually the 7.5 nanosecond time step of our FPGA in order to capture these switching transitions. And then we do a time averaging approach where we do that over one time step. So the model is actually running at 5 microseconds, and then the grid is at 25 microseconds. So there's a lot of good details and nuance in terms of how this is implemented. There's a great paper that I can send you if you're interested in learning more. But for now, we can kind of abstract that away. One other thing to note here is that these signals are accessible for you. So if you want to say manipulate this and model a gate driver failure or something in one of these switches, we can manipulate these signals in some way in the schematic in real time. So what we actually have here is this enable or disable signal, say representing a gate drive enable circuit, and then only after that is turned on, then we'll see these switches actually modulating our converter. So then we also have current flowing out of this unit, and we have a measurement here. So we're just tagging these symbols here. So IUVW is the current flowing through this RL branch, and we'll send it to an analog output. So each analog output, if we just open this up, it has a set of different channels we can use, as well as scaling and offset parameters. So it basically transforms our the measured circuit quantities into a range that's usable by our controller. And so if we look at this actually at the top level, so notice this is IUVW, and if we open this here, we see that there's this port created at this level as well, IUVW. And so this is automatically created when you include this analog output component into the subsystem. So down here, we also have these SFP signals. And so this is what's used to exchange information between these RT boxes. And it's kind of the mechanism by which we electrically couple these systems by exchanging information between the two. So what we have here is the signal going out. And so we're measuring the voltage across these capacitors here. And then we're sending these out as data packets to the other RT box. And then what we're doing is we're actually taking information in from the other RT box, from the grid, and we're saying how much current is leaving our converter, and then we inject that back into our capacitors. We also have a few other signals here, so VG and IG, and those are just used for controls and plotting purposes over here. So let's open up the the grid side, and we'll see how this is implemented on the other side of the converter. And so we can just minimize that, and we'll open up the grid. And so we see here is the SFP signal coming in, so SFPB in, and we see the voltage that's at the capacitors over here. And if we were to open this, we see it's applied as a controlled voltage source. And so we can see the current leaving this voltage source, what's going through this RL element here, and then we can re-inject that back into the capacitor. So one thing to note here is that, some topology, this may not be the best location to split it. It may be necessary to split it somewhere else. It's because in this case, the capacitor current is a capacitor voltage, and output is largely a grid frequency. And so a bit of latency between these systems isn't critical in this application. So also, I just want to highlight quickly the controllers here. So we have these 3 different controllers, and these are the TI C2000. These actually implement some of the control logic from our TI C2000 target support package. And I don't want to get into too much detail here, but one thing to note is that all of these models are actually executable. And so we can just go to simulation, start, and we can run all these models offline. So we can actually see that we're updating these scopes in real time and we're simulating these. And so with that, just to explain, I'll let this run while I talk through this one a little bit. So what's happening in here is that we have these different ADCs, and we're sampling them, and they're transformed into different voltage and current values. We transform these values into the synchronous reference frame, and so there's a little PLL in this subsystem. And then they're fed into this dual cascaded controller. And so you have this voltage reference come in, you have this VD and VQ control, and then you have that fed into a current controller, so IDIQ, and then it goes through a space vector modulator and then is ultimately set up and configured to PWM outputs of our controller. The other thing to note here is that we can actually toggle the mode. So right now this one is in current control, but we can just set it to 0, and it basically just switches from taking in this fixed current reference or taking in this fixed voltage reference. And then naturally on top of this, you could say implement some type of droop controllers or other more sophisticated local controller. Just the idea here is that these are actually, reasonable controls that are executing on these models. So with that being said, we can also just take a quick look at the model here and see while this has been running. So at 0.5 seconds, we'll actually see this turn on, and we should see the response of our current regulator. So this is a turn on transient of our current regulator. And again, these VD and VQ, we're operating in current control mode, so they aren't very relevant. But we can see that we, have a pretty good settling time, and that this model is actually working, controller is actually working fairly reasonably well. And we can also, again, look at any one of these subsystems here, and we can see that, what is this transient here, how are converters starting up, and look at what's going on with the synchronous generator unit as well. And so the idea is that this offline model, it contains a lot of details and actually in terms of how these controllers are implemented, but it is very high fidelity and can be run offline to investigate these systems, say before moving real time. Next, what I want to do is actually start building this model, and we'll start to take it real time. And so in order to do that, what we use is our coder, Plex coder. And so as mentioned earlier, this takes the continuous state space models of our controllers and subsystem, and it transforms them into the discrete state space, generates ANSI C code describing them, and then we use these target specific libraries. So it tells the RT box how to configure an analog output pin, how to map these digital inputs to different signals. And so we package that up all into a compiler, into an executable, and we'll put it onto the RT box. And then we can also do that again for other real-time targets. And so what I want to show is these models are all set up so that they're going to start at the same time. So they're initialized with a common state, and we can see synchronize their initialization. So let's start, and we'll build this model. And again, so this is synchronized with units A, B, and C. And so this is calculating it, and it's going to write the output. And then we should slowly see this blue light start blinking here once the model is deployed to the unit, but then waiting for the other ones to start up. And so similarly, we can do that for VSI-A. And so we can see that we're connected to this VSI-A target device. We're waiting for this SFP-A signal to come in from the master before we actually start. And so that one's done. And then we can go on to the next one. So there are also a few other signals set up here. So we can specify the analog and analog output ranges, input ranges, digital voltage levels. and configure our RT box, as well as specify the discretization time here. And so if we look over here, we can say that we're operating at in this case, it's going to be 5 microseconds. A TS plant is 10 microseconds. And so with that, they're all started. And so we can actually see here, these lights went from blinking blue to solid green, solid blue. And we can see that our scope is actually showing a 3-phase voltage waveform at the connection point of VSI C. And so now what we can do is we can actually start to connect to these units in external mode and see what's happening. And so if we just go to this external mode tab and we're connecting to the grid box, and we can activate auto triggering, and we're basically, that means that we're transforming this Plex schematic into like a real-time scope and interacting with the calculations and model running on this RT box. So we can also connect to all these units at the same time. So while we're there, we'll just connect to these two. And so we can look and see and look at the scopes here. And so what we're looking at are the current signals. So for each converter's output current, and then the synchronous generator output. And so right now, all of these controllers are off, but what I can do is say start to manipulate these switches and enable this controller. And so we can see that this converter A is regulating the output current to about 40 amps peak, and we can say start to manipulate and see how these other controllers turn on. So we can turn on this other controller. Again, it's operating in a similar current regulation mode. And then we also have this third converter here, which is operating in a different mode. And one interesting thing we can see here is actually these slower mechanical time constants of the synchronous generator. So if you saw that kind of pulse up and down, that's all these different things happening at the same time. So you have these switching converters modeling, you have this slower time constant of the synchronous machine, and it's all being modeled in real time. And so if we actually want to just look at the VSI B subsystem here, we can see how this control is working. And so I actually have to go and turn on auto triggering on this one. And we'll see that these scopes are updating in real time. And so you can see these are actual switching waveforms. We can see the current ripple on that converter side inductor, as well as the filtered current that's being injected into the grid. And again, we can manipulate this on and off and see how our system starts up. So we can also interact with things that are happening at the grid level. So we can explore how the system is running on a phasor diagram here. And so we can see this green unit here represents the point of connection, this fixed voltage, and then these are the outputs at each one of these PSI converters, as well as the synchronous generator output. And so, we can start to manipulate things on this subsystem here. And so if we open this back up, we can say start to change our field excitation from value of 1 per unit to, we can change it and see again a bit of a transient here as this mechanical, our synchronous machine basically adjusts to a new operating point. We can see this transient slowly die down. So another point here is we can also manipulate and interact with this model, not only through this user interface, but we can also program values. And so one example here is just this programmable value that we set here. And so this is used to say toggle the load value. So right now this switch is open, but if we were to interact with this, we use a platform called XML RPC. It's kind of a generic server interface, but we can interact with that through Python. And so if we were to open up our Python IDE over here, and we were just to, let's move this back over to our Plex. And actually I can grab this and just slide it over. And so we can see right now that this programmable value is set to 1. And then we can basically open up a socket to the server operating on the RT box, and we can say set a value. And we'll see that that's 0 change to a 1. And again, this is super basic, but we can use this to say set up certain trigger conditions to capture a test case that we're interested in observing. And then we can also connect these, say, with a data capture block, where we can have it trigger a scope in Plex and export it that way. So again, it's a flexible platform, just showing that you have kind of all of this core functionality where you can interact with this model in real time, get data, and have really high fidelity converter models interacting with these power system components. So whether these are replaced with an AVR or with a governor, again, you can start to build up this model into something that's a better representation of your system. So with that, I think that includes most of the content I wanted to show today. I can summarize real quick just what we went through. So we did a quick introduction to some fundamental microgrid concepts. We did an overview of how Plex tools are being used in microgrid applications and talked about the value of hardware-in-the-loop testing. So there are a few DER and microgrid models that I showed that I invite you to look at in your spare time. And then we also did just a brief demo of a hardware-in-the-loop testing of a small microgrid operating in real time. So it included several different DER controllers, and we just highlighted the real-time workflow and this multi-purpose model structure. And then each one of these RT boxes, again, can be kind of broken down. This system can be broken down into several individual units and then repurposed for other projects or larger or smaller scale hill systems. So with that, I just want to see if there are any questions that I can ask, and feel free to ask them right now in your chat window, and I'll be happy to address them. Sure. So one question is what is the largest size network that can be simulated on an RT box? And so for us, it's difficult to provide a limit in terms of the number of, say, electrical nodes because the RT box performance requirements are so application dependent. And in practice, it's about finding the balance between the simulation time step that captures the effects you're interested in. So say have that as an upper bound, and then how you balance this out with processor utilization. If you have a Plex coder license, you can run this discretized model offline and see what simulation time steps you need and get an approximate feel for the model fidelity that you need and benchmark this against, say, a variable step solver. And then I also want to mention that the role of the applications engineering team here is to help you answer these questions. So we want to see if our solutions are appropriate, maybe what your hardware requirements will ultimately look like, and basically test out and validate the system as a proof of concept for you and if it meets your needs. Another point is that we also offer design services. So say if you need a certain interface hardware or you want custom model for your hill project, that's something that we can also work with you on. So feel free to reach out to us at info@plexim.com if you have a question in that. Great, and so there's one other question. So what are the delays introduced when using fiber links to interconnect RT boxes? And so that's another good question. So SFP communication introduces a latency of 2 simulation time steps. So model B processes the information from model A about 2 time steps after it's processed by model A. And one thing to know actually is that in offline simulation, these models are models explicitly. And so if we were to look at this SFP port here, if we were to look underneath this subsystem, we'll actually see that there's a delay included here. And so we model this delay and see if that, say, will impact our stability. And another point to note is that when you have these connected in series, then the communication doubles basically. So if you have box A to B and B to C, then the communication latency for a bit of information from A to C is about 4 time steps, including 2 hops. And so with that, I wanted to say thank you for attending this webinar on microgrid applications in Plex. And we'll be sure to follow up with your questions and feel free to reach out to me or Plexim at info@plexim.com. Thanks for watching.